I chatted about it briefly. It hasn't been released officially yet, but someone was just interested as to what it would be. So I'll just tell you informally what the first assignment is. It doesn't get released till next week. The first assignment is we give you some programs, which you run. Good stuff, you've moved. Well done. Who else moved? You know, I find if you stay in the same seat, you're just like, you're going to, you know, has anyone ever had a plumber come to their house to do something? And he's wearing the same clothes he wore when he was 20. And it looks ridiculous now. And his music, when he turns on the radio, they're the songs that were popular when he was 20. He's fossilised at age 20. I think that happens if you just don't move. You just, suddenly you fossilise. So you've just got to keep moving all the time. And it's good for your brain. So the first assignment is we give you some programs. You run the programs. We don't give you the source code. We don't give you this. We don't tell you what the algorithm is. We just tell you what the problem is. This program sorts numbers. And you run it and you can observe it. Look at what's observable. It's observable behaviour. And you tell us, oh, what algorithm this program uses, probably. Anything you can tell about the program. You might say, oh, it's bubble sort using a list. Oh, it's insertion sort on an array. Oh, it's oblivious bubble sort. Oh, it's bubble sort with early exit. Oh, it's crazy sort. Okay. And so by the time the assignment comes out, you'll know many sorts. Okay. Are we ready to start? Does anyone have any more questions before we start? Okay, let's go. We were then, what we just did then, with this, we were timing how long things took. So, what were we measuring? What were we measuring? Process. We were measuring properties about the process. What do we want to reason about? Remember, we've got program, algorithm. Start again. We've got, you tell me. We've got a problem. We've got a problem to which we come up with an algorithm, which we implement and get a program, and we run it and have a process, or multiple ones. So when we're timing, we're looking at processes, and we want to reason about algorithms. So we've got this problem that there's a couple of layers of crud between where we can measure and what we were interested in. So if you just measure the amount of time, what other factors can hide what algorithm it is? Suppose we run a program. Oh, okay, you'll answer first. Let me just do the suppose thing first. Suppose we run a program. I tell you this is a sort algorithm. Yeah, you got your first assignment. It's run the program sort number 7. You run sort number 7 and you give it 1 million items to sort. It's correct, you check it's correct, but of course it's going to be correct. Actually, maybe that would be one of the funny algorithms to put in. So its observable property is that it's not correct. So you could call it incorrect sort. I think that's a good idea. Okay, so you run the program and it takes 1 second to sort 1 million things. Why does this stop us being able to say anything about the algorithm? What were you going to say? Say your thing first then, sorry. Oh, you were just stretching. You were pointing. Look at that idiot down the front. He's got a hook, it's like Peter Pan. Yes?
Well, we need to know more like different number of sorts in order to actually graph it and find out how it grows.
That sounds really good. Can you say that again, differently?
Well, if we did it, we did say for every item between 1 and 1 million, then we could graph it and see how it grows.
Yes. What's your name?
Cameron.
Cameron, yeah. Cameron's got it in 1.
Time to place the team.
Wow. Someone's getting the sorting hat. Oh, money.
I have it.
No. I want the sorting hat. No, he's exactly right. If we run a program, you run your program to sort the 1 million things and it takes 1 second, it tells you nothing. Because there are confounding factors. The confounding factors being what? What could make it take different amounts of time? Yeah?
The measurements or whatever it is.
Yeah, what the machine you're running it on, the properties of the machine you're running, absolutely. What else might confound it?
I've been listening, but the way the list of the items are given to solve them.
Oh yeah, the actual specific data, like maybe remember Chris? Yeah, Chris pointed out that a bubble sort with early exit works well if the data is fairly well sorted. So maybe we'll get differences in time based on the actual properties of the data we give it to sort. Yeah, that could confound it too. How would we solve that problem? Give it lots of different ones and average it or something. If we were a scientist, I guess we'd try and rule things out that way.
Do we look at the worst case?
Construct particular cases that we think push it to its limits. Yeah, this is the sort of things a scientist would do. That's very good. So, yes, Cameron was right. Rather than just looking at the speed of when we run it, because that doesn't tell us anything, we're really interested in how the speed changes as what we tell it to do changes. And hopefully this is very visual here. The fact that the algorithm took less than a second to solve the fourth thing really tells us nothing about this at all. Do you agree? Even the fact that to work out 11 things that we took roughly the same amount of time, that doesn't tell us anything. If that was the only thing you were looking at, you'd say, oh, they're probably the same algorithm. It's actually not the time it takes that's the least bit important. Because the time it takes depends on the machine speed, depends the language it's written in, depends the actual chips that it's running on, depends on how effective the compiler is, depends on this whole range of other stuff. We want to find properties that are not dependent on the program or where we're running it on, properties that only belong to the algorithm. So how we do that is we say, gee, what happens when I, say for example, double the number of things I'm sorting? I used to do 6, now I do 12. How does the time behave on Thurston's program? It doubles. So doubling the input gives me double the time. What's that relationship called? It's a linear relationship. On my program, what happens? I double the input, how much longer does it take? Whoa, a lot. 1,000. So does that look linear to you? No, it doesn't look linear to me either. Maybe it's quadratic. Maybe it's exponential. Maybe it's cubic. How many points do I need to know if it's quadratic or not? 3. Got to take 3 measurements. How many to know if it's cubic or not? 4. How many to know if it's an nth degree polynomial? How many measurements do I have to take? N plus 1. Okay, so I'm going to have to take a series of measurements. I'm going to have to start sort of trying to deduce how the time it takes changes as the size of the input changes. So that's what I claim measuring program complexity is all about. Well, let's look at our intuition. Why do we measure complexity that way? What we're interested in is the relationship between, here's my algorithm, how complex the problem is, how complex the problem instance is, and I'm interested in the relationship between that and how much work my algorithm does. So the problem instance, what do I mean by problem instance? Like if I'm sorting numbers, a problem instance is sort the numbers 1, 2, 5, 7, 8, 3. That's an instance of the problem, the general problem of sorting numbers. That's solving that particular set of numbers. 1, 2, 5, 7, 8, 3. That's sorting 6 numbers. So our intuition is, in everything in life, certainly if I ever gave you an algorithm to carry out, the amount of work you're going to have to do depends on how complex the problem I give you to solve using that algorithm is. So if I say, can you please sort all my books into order on my bookshelves, you're very interested to know how many books I've got, because that's very clearly going to make a difference. At the very minimum, how much work is he going to have to do? No. I don't care actually how much work. I mean, I'm sort of hunting the relationship. If I've got n books, how much work is he going to have to do? No, the minimum. What's the minimum he's possibly going to do? He can't get away from doing n. He can't get away from doing n. If I've got n books, he's got to do at least n things. So sorting Richard's books is not going to be better than linear, because you're going to have to touch each book. And there's n of them. So you're going to have to do n bits of work. And maybe it's going to take a whole lot more. Maybe you're going to do the insane bubble sort thing, and you'll be spending all day swapping books on my bookshelf like this for hours and hours. And you'll end up doing roughly how much? If I've got n books, how many swaps will he have to do? N outside of n minus 1 on 2. What if I've got 1,000 books? What's the value of this? Now here's where we deviate delightfully from science. Because we don't really care, because we're computer scientists. So if I say n times n minus 1 on 2 for 1,000, what's that?
500,000.
I'm prepared to accept 500,000. Insert the word about in front of it. That's about 500,000. In fact, I'm prepared to accept it's about 1,000,000. It's about n squared. Can you see that this is going to be n squared on 2 minus n on 2. That's the amount of work we're going to have to do. And as n gets really big, what's the most important term there? N squared. Now the divided by 2 is sort of irrelevant, isn't it? Because I've got this ephemeral notion of work. I haven't even said what work is. What's work? Is work, is picking up a book 1 bit of work or 2 bits of work? Pulling them out and swapping them, you could argue that's several bits of work. There's a pulling out, and then there's a pulling out the other one, and then there's a putting in the putting. You could say swapping is 4 bits of work. Or maybe you have to put one of the books down when you swap and it's 5 bits of work. I don't really care. All I care is, in general, it's a sort of n squared bits of work. What I really care is, if I double the number of books I've got, what happens to the amount of work you've got to do? No, well, it's more. If I double the amount of work you've got to do, if I double the number of books you've got to sort, what's the increase? This is the $50 million question. So if you've been asleep the whole lecture, suddenly wake up now and go, oh, I'm about to learn what the whole lecture is about. If I double the number of books I've got to sort, what happens to the amount of work you've got to do? It quadruples. It goes up by 4. Can everyone see that? Let me do the elaborate maths. This is the only bit of maths we'll ever do, I promise. The amount of work that Clifford had to do before was however much work it takes to actually do a swap. How much work does it take to do a swap? It takes k work to do a swap, say, because I'm not going to care about it, so we'll just make it some number. It takes k work to do a swap, and how many swaps is he going to have to do? Well, he's going to have to do n minus 1 times n all over 2. And if I calculate exactly how much work that is, we'll find that's kn squared over 2 plus minus kn over 2. That's how much work you've got to do. I don't know what k is, so you can see why I didn't really care about the 2 in a way, because I don't know what k is. Let's just forget. We normally just forget about constants. But at the moment, suppose we did magically know what k was. We knew exactly how much work on the actual machine we're running it on it took to swap 2 things around. Then it will take that amount of work. Now what if I then say, actually, you missed the other room. I have twice as many books. I actually own 2n books. And actually that's true. I do own 2n books. So how much work are you going to have to do? Well, you're going to have to do k times 2n minus 1 times 2n divided by 2, which is equal to k for n squared divided by 2 minus k to n divided by 2. Now, if n is really big, what's the relationship between this term and this term? This is enormously big and this is sort of trivial. So let's just think, well, if I'm forgetting what k is and I'm ignoring 2, probably don't really care about this. So for all intents and purposes, I can sort of rule this out. At the limit, as n gets bigger, this term is completely swamped by this term. So roughly, the ratio between these 2 terms will tend to the ratio between this and this. Now what is this? Well, let's do it the other way around. What is this divided by that? 4. Yeah, everything cancels out, doesn't it? I love it when that happens. See, we didn't care about k, and it doesn't matter. It's cancelling out. N squared's gone. There's 1 and 4. So if I double the number of books, I have to do 4 times as much work. This is a characteristic of a quadratic algorithm. If you double the complexity of the problem instance, double the size of the problem instance, you quadruple the amount of work you have to do, which means, presumably, if each amount of work takes a fixed amount of time, you quadruple the amount of time it takes to run. Now, what would you rather have, a linear sorting algorithm or a quadratic sorting algorithm? Both. Because you're a collector. Who said both? You did? Let's pretend you did. Why both? It's a bit cruel of me, wasn't it? Yes, shoot.
Because quadratic is more effective up to a certain point than linear is, and linear is better.
It's a very nice answer. What's your, I actually know you. I can't remember.
Jackson.
Jackson. Are you the guy that mailed me? No, I spoke to you yesterday. That's right. Yeah, if I was in my vague graph with without specifying units, oh, excuse me, here's my problem instance size, and here's how much work I do. Well, not me, how much work Clifford has to do. A quadratic one is saying that the curve is something like this. I can't have a negative number of books. That doesn't actually look like a parabola, but let's suppose it is. Depending on the constants that we stick in here, it's something like that. And a linear amount of books means it goes up at right angles, doesn't it? How does that happen? It's got to be a diagonal, but I want to make it do what I want it to do. What have I done wrong with?
The curve sits on the origin because there's no constant back.
The curve has to sit on the origin? Oh, no, there's normally a bit of overhead when you run a program. Even if you do nothing, it takes a while for the program to wake up, realise it does nothing. Make the curve curvier, or start up here maybe. Yeah, let's start up here. There we go. But as you know, curves can intersect lines at 2 points, but I didn't want it to do that. So, depending on the constants, maybe initially the linear algorithm's actually slower. Like Thurston's one was. Yeah, he had a linear algorithm, it was initially slower because it was running on a crap machine, so he had really big constants. So that was a straight line, its growth was really nice. It started off really bad, but slow and steady won the race, didn't it? Because although it started off bad, it only grew slowly. Whereas although this started off super fast, the sheer amount of work, the complexity the algorithm made it do, because the algorithm just generated too much work, it doesn't matter that the person doing the work was the world's fastest person. Eventually, the amount of work they had to do just completely swamped them, and Thurston, who's very, very slow, but doesn't do very much work, gets to win. Does that make sense? So it's not clear if you want a linear one or a quadratic one. You probably don't want a simplistic answer to that. The general answer is, if you've got a small instance, and you only have to worry about small instances of a problem, then the algorithm complexity doesn't really matter. And you look at all the other fine-tuning and optimization stuff. And that's when I'd be quite happy to use, say, for example, a bubble sort. If it was sorting small numbers of things, I could write in a few lines, it's guaranteed to work. But if it's ever going to get to sorting a large number of things, then whoa, it's going to be n squared. I wish I had a faster way of solving it. All right, is everyone cool so far? All right, now I have a puzzle for you. I won't do it on the, let's not look at that, I'll do the puzzle on the blackboard. I have some friends who talk to me when I take my tin foil off. And two of them come from Mars, and they're married. There's a Martian man, and there's a Martian woman. And the other two come, of course, from Venus. And there's a Venusian man and a Venusian woman, VW. And my good friend Raymond Smulian told me something I'd never noticed before, that the Martian man always tells the truth. And the Martian woman always tells a lie. Never ever tells the truth. And the Venetian man always lies, and the Venetian woman always tells the truth. Now, unfortunately, because they talk to me but I can never see them, I don't know who's who because they all sound the same. I'm too embarrassed to admit it. Suppose one of them's talking to me, and I want to work out what planet they came from. Can you think, don't call it out, just write it down. Can you think of a simple yes-no question I could ask them which would give me enough information to work out what planet they came from? Just write it down. One question, yes, no, to work out what planet they came from. What's your question?
Are you guys asking one of the four?
I'm asking, no, don't call it out. What does don't call it out mean? It means don't call it out. Shh, write it down. Type it in. Type it in. Type it in. Don't call it out because everyone wants to work it out. What was your question? It was,
Are you talking to one?
yeah, I'm talking to one of them. Well, they're talking to me. What's that?
What gender they are?
No, I don't know anything about them. I just know they're one of my friends from another planet. And don't make fun of them. Okay. So I can ask them one question. I need to work out what planet they come from. What question can I, or is there even a question I can ask? A simple yes, no, well there is. What yes, no question can I ask to find it out? You know it? Write it down. Put up your hand when you got it. Already one person's got it. 2 people have got it. 3. 3 people have got it. 4, 5, 6, 7, 8, 9. Okay. 10. Someone want to say what it is? Yes, you can. Hang on. Yes, you can.
So are we just trying to see if they lie or they're not lying? Is that...
You got to work out what planet.
You got to work out what planet they're from.
all 4 of them or just 2 of them?
No, I'm just speaking to one of them. I don't know which of the 4 it is, and I've got to work out what planet they're coming from. Go back to thinking. Yes?
Can you tell the men and women apart?
No, you can't tell the men and women apart. You know they're Martians. It's really offensive. Yes?
Would your partner say you're from Mars or Venus?
Thank you very much. They are married, actually. All right, let's try that. Why not 3? Why not 3? We can't question their ways. That's really good, by the way. What's your name?
Jay.
Jay's got it. Okay. Well, Jay's got 1, but it's my favourite one. It's got to be yes, no. You want to rephrase it to be yes, no? Yes, it does. Would your partner say you're from Venus?
But if you're asking either of them and then
I'm only asking one.
you're only asking one,
I'm only asking one of them. No, you have got it. You have got it. Asking if them, you see, what I'm trying to say, because it's a really good point, so I want to say it to everyone. If we're asking a question that says, do they come from Mars or Venus, how many options are there? 2. So if we ask a question that allows them to have a yes-no answer, can you see we can map that onto the same options? It's a 2-way answer as well. Would your partner say you come from Venus? Let's have a look. What happens if they say yes? They're Martian. Whew, better try all possible combinations, hadn't we? Luckily, only 4 combinations, so we can brute force it. Would your partner say you came from Venus? You're a Martian man. So your partner's a Martian woman. Would the Martian woman say she came from Venus? Yes. Would the Martian man report truthfully what the partner would say? Yes. So the answer would be yes in that case. Suppose you accidentally asked the Martian woman, would your partner say that you come from Venus? What would the Martian woman, what would the Martian man say? No, he would say the truth. Would she accurately report what he would say? No, she would lie about his saying no and she would say yes. The Venetian man. Let's see, we're asking him, so what would his wife say? Do you come from Venus? She would say yes. Will he tell the truth about that? No, he will lie about that outrageously. Suppose we ask the Venetian woman, would the Martian man say that he comes from Venus? Sorry. Would the Venetian man say he comes from Venus? No. Would she tell the truth about that? Yes. So again, a no. So if we get a no, this is the irony of this whole extraterrestrial thing. If we say, would your partner say you came from Venus? Whatever they say is going to be the wrong answer. If they say yes, well, they're not from Venus. Can you think of a way, by the way, you could change that question so you didn't have to do that final inversion, which Max, where I'm... What's that? Insert a not in there? Yes. Yes, my girls are good at doing that. But try another way. Because it's making it more complex. Oh, well, it's a challenge for you to think about. Because now I have another question. What question could I ask them? I'm speaking to someone. I don't know which one. What question could I ask them, a single question could I ask them to work out if they were male or female? No, Martians and Venetians speak English. Yeah. They actually speak American English, which is very annoying. There's nothing we can do about it. So what question could you ask? Quickly thinking, is everyone thinking? You've got it? Yes, would your partner say you're a man? That's perhaps not a question to ask people, but a real man. Would your partner say that you're a man? Yes. And would we believe what they say, or would we do the opposite? I don't know, we'd have to work it out. Probably we'd do the opposite. Have you worked it out? It is the opposite? Well, I don't know. Might be. Yeah, could be. I mean, it's very plausible. Without checking it out, I wouldn't be 100%. Because I'm sceptical because I'm a scientist. Well, a computer scientist. Okay, last one, and this is the hardest one, so I certainly don't want to... Oh, did you have something to say?
Does your partner lie?
Does your partner lie? Oh. Okay, does your partner lie?
We'll say yes.
He'll
say yes.
Everyone will say yes. Yeah. But that's good. No, but keep thinking. I like the way you're trying to think. Single question. Oh, yes? You could ask them if they're from Mars? Yes, you could ask them if they're from Mars. That's very clever. But we'll have to track it through. But I believe that's right. If you ask them if they're from Mars, it will answer whether they're male. No, oh. No, it won't. No. You got to... let's see. Do you come from Mars? If he's male, he'll say yes. If he's female, he'll say no. If male, she'll say yes. Oh, brilliant. Female, no. Not even need for an inversion. That's very nice. Well done. What's your name? Norris. Well done. Last question, and everyone except Norris, you're not allowed to do this. You're too good. The question is this. One question. What question can you ask them? Yes, no question. That when they answer, you can work out their gender and their sex. Put up your hand when you got it. This is the hardest of them all. They're making suggestions. It's confusing me. Shut up. I'm listening to the students. What's that?
They only answer once.
They can only answer once?
Answer from the two possible outputs. You
Yes.
two pieces of different information.
Thank you very much, Chris. Ask your question again, even more loudly. In fact, say it into my microphone.
You have two answers, and you have four states. They can't give you enough information.
Yes, thank you. What are the possible answers they can give us? Yes and no. How can we use that piece of information, which only has a two-way choice, to distinguish between four states? Can we do it? No, we can't do it. When we talk about information, this is an information question. When we talk about information, we describe information in bits or binary units. There's an interesting study called, from Claude Shannon, who looks at the theory of information. He's a very, very clever guy. Brilliant guy, in fact, from probably more than 50 years ago, a long time ago. Information theory. So the idea is, asking a yes-no question gives us one bit of information, which lets us accurately describe how many possible states? 2. If we wanted to be able to describe up to 4 states, how many bits of information would we need? 2 bits. A lot, rounded up to the nearest lot. 1 rounds it up to the nearest lot. Yeah. If we had to distinguish between 10 possible states, how many bits of information would need to be available in our questions? How many? 5? No? 4? Why not 3? Because with 3 bits of information, how many combinations are there? 2 to the 3. Shall I write them all out just to make it really clear if you can't see it? With 3 bits of information, the first bit of that's the same as me saying you're allowed to ask 3 yes-no questions. Okay? You've got 10 Martians in a room and asking only 3 questions, how can you tell which one is the counterfeiter? You know, that famous logic puzzle. You can't do it. Because why not? Because the 3 questions, you're going to get either yes or no for the first question, And then if they say yes to or no to the first question, they could say yes, yes. What are all the combinations to the questions? Question 1, question 2, question 3. They could say yes, 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 no, or they could say yes, no, yes, or they could say yes, no, no, or they could say no, yes, yes, or they could say no, yes, no. Have I got it right? No, no, yes, no, no, no. Okay, 1, 2, 3, 4, 5, 6, 7, 8. There's only 8 possible combinations of answers they can give. So using their answers to those questions, we can only sensibly distinguish between 8 possible configurations. Is that clear? I mean, it's just by counting. This is called the information content of those answers is 3 bits. And that allows us to distinguish between 8 states. Now, oh, Richard very cleverly nearly rubbed it out. Here it is. Our whole mission in this course is to grapple with this dilemma. Given how complex the problem instance is, how much work do we have to do? And I've talked about work already. We don't really know about work, and it depends on the machine and all sorts of things. We're happy to make outrageous approximations here because we just don't know, and we'll just round things off and we'll put constants in and we'll just be very relaxed because we know however much work you come up with when you answer the question. If you actually had to precisely say how much work, then you could run it on a computer 1,000 times faster and it would only be 1,000 times a thousandth of that amount of work. So we don't want to pick an actual number here, we just want to get it roughly. But what about this side? How complex the problem instance is? Well, let's look at it. You're sorting 1,000 books, or you're sorting 2,000 books. What's the growth in the amount of information going into the problem? 1,000 books, or 1,000 integers, if we want to think about sorting integers. You've got to sort 1,000 integers, or you've got to sort 2,000 integers. What's the difference in the amount of information we're giving to the sorting algorithm to describe that problem? Because how complex a problem is, yeah, can you see this, is how much information it takes to describe the problem. If you can describe it really quickly, it's a simple problem. If you can say sort the numbers 1, 2, 3, that's a simple problem. If you have to say sort the numbers 1, 2, 4, 7, 9, 8, 3, 6, 5, 2, 1, 7, that's a more complex problem. So, how much, well, someone say, what's the relationship between sorting 1,000, what's that? Twice as many, yeah. One, I'm giving you the names of 1,000 DVDs or books. The other one, I'm giving you the names of 2,000 DVDs. If they're all, roughly the average length, then the amount of data I'm giving you is roughly twice as big. That fully describes the problem. Is everyone cool with that? So when we are interested in this relationship between input and output, we're interested in the amount of information going into the problem, into the algorithm, and then the amount of work it does. Is everyone cool with that? Please ask a question, because I'm now about to give you the final bit that at first sometimes doesn't make sense, which is why I'm going this long, slow, tedious, simplistic way of explaining it. But please ask if anything there doesn't make sense. All right. I'm asking you is 7 a prime? The problem is n a prime? The instance is 7 a prime? I stick that into the algorithm and it takes a certain amount of work. I know it takes 100 bits of work. I'm now going to plot it to work out what the relationship is between the instance of the problem size and the amount of work it does. What is the size of the problem? Suppose if I put in is 7 a prime, suppose it takes 7 seconds to solve that. And then I say is 8 a prime? And it takes 8 seconds to solve that. And then I say is 9 a prime? And it takes 10 seconds to solve that. What does it look like? What's the relationship between the size of the input and the amount of work it does? I wanted you to say linear. Who said linear in their heads? Who was thinking linear? It's the natural thing to think. But it's not. What am I sticking into my algorithm? When I'm sticking 7 in, what am I sticking in? I'm sticking a prime in, I'm sticking in a number. How big is that number? How much information content is in that number? How many bits does it take to represent that number? 3. If I stick 8 in, how much information do I have to give the algorithm before the algorithm can give me an answer? I have to give it 4 bits. If I stick 9 in, I have to give it 3 bits, 4 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 bits, and 5 bits. Can everyone see that? So when we're talking about the complexity of a problem, if I'm specifying a single number as the input, and the amount of work increases linearly with that number, it's actually increasing exponentially with the number of bits that it takes to represent that number. Because
It doesn't matter though, doesn't it? Because the bits go up like 1, 2, 4, 8, 16. It doesn't go up like 1, 2, 3, 4 in a computer as such. Unless you're like packing headers or something.
So it doesn't matter for small instances, because if you're reading in an int, it doesn't matter what number you stick in 1 to 32, probably the computer's actually going to literally take in 32 bits each time. But like, for example, with the problem Thurston and I were dealing with, where we had to print out those numbers and find those big numbers, they very quickly grew beyond the size of an int. And they grew beyond the size of a long, and then they grew beyond the size of a long, and they grew beyond the size of an unsigned long. And so both Thurston and I had to write an ADT to represent numbers of variable size. And that's why my code called a couple of funny functions rather than just doing it straight away with arithmetic, because I had to deal with each digit separately. So sure, for small values, down the end, it's a constant and we don't care. But as the input size grows, it quickly overflows any constant size input. And we would say this algorithm, to work out if a number is prime or not, is not a linear algorithm. Whew. To work out if 7's prime, what do I have to do? Naively, I could just check if it's divisible by 6, by 5, by 4, by 3, by 2, by 1. So I could do 6 divisions. And to do 8, I could do 7 divisions, and to 9, I could do... So literally, it is something linear. It takes, naively, 6, 7, 8 calculations to work out if it's prime if you're doing it brute force. Now you can think of optimizations. You can think, oh, I only have to start halfway down, or I only have to start at the square root, or something like that. But it turns out those optimizations don't make very much difference, because the amount of work you have to do to tell if a number's prime is still growing roughly linearly with the number, or square rootly with the number. Let's just suppose it's linearly with the number, which means growing with the number of bits coming in, it's growing exponentially. Which is sort of why computer security works. Computer security works because it's very hard to factor numbers. And if you give me a 1,000-bit number, it's very hard for me to work out what factors it has. Because how much work do I have to do to check all the possible factors of a 1,000-bit number if I was going to do it brute force? A 1,000-bit number. How big is a 1,000-bit number? How big? 2 to the 1,000. Somewhere between 2 to the 1,000 and 2 to the 1,001. So think of the number 2 to the 1,000. That's an astonishingly large number. How much work would you have to do to check all the possible factors? Well, you'd have to do 2 to the 1,000 bits of work. The universe is going to stop before you've done 2 to the 1,000 bits of work. Thank heavens for that. Most modern security, most cryptographic methods rely on the fact that you give me 2 numbers that are prime, I can multiply them together and work out the product straight away. So going that way is really easy. So I pick 2,000-bit numbers, I multiply them together, I get a 2,000-bit number, and it's only got 2 factors, because I multiply 2 primes together to get that number. I make that number publicly available to the world. Modern cryptography fails as soon as someone can work out factorize that number. That's how RSA fails, if anyone can factorize that number. And that number is publicly available for everyone to look at. But no one can do it, because it takes too much work. It's too hard to do. You'd have to write a computer to do 2 to the 1,000 operations. 2 to the 1,000 is a very, very big number. If you did half as much work as 2 to the 1,000, how much work are you going to do? 2 to the 999. Not 2 to the 500, 2 to the 9999. You just take 1 off if you've done half as much work. So you write a really clever algorithm and you tell me, Richard, I got a doubling. I got a speed up of 2. I say, oh great, now we've only got to solve 2 to the 99999. You run it on 1,000 clusters. A 1,000 core machine. 1,000, what's that? That's 2 to the 10. So you've only got to do 2 to the 990 now. The universe is going to start and stop 1,000,000 times. It's going to completely go grey and then start again and completely go grey and go start again. And it's going to do that more often than you've got hairs on your head before 2 to the 999 will actually ever run to execution, even on my Mac. So we are very interested in the complexity of algorithms, because if you get it wrong, then the universe will stop before you will get the answer. And if you get it right, then you can get the answer very quickly, even if you're running on a crap machine. So does everyone understand? This is the subtlety. If the number coming in is just a single number, don't think that represents the size of the problem. The size of the problem is the number of bits it takes to represent that number. If you're sorting 1,000 titles of books, the size of the problem is the number of bits it takes to represent those 1,000 books. That'll be proportional to 1,000. If the average number of characters in a title is 10, and you've got 1,000 of them, that'll be 10,000. So in that case, it is proportional to n, but when n's a single number, it's just proportional to the number of bits in it. Am I saying the same thing over and over again, or does it make sense? Yes, it makes sense. Does anyone have any question to ask about that? Because that is all I wanted to say. Any question at all? Yes, up the back. How many bits do you need? How do you work that out? What do you mean? Oh, binary, just a binary question. That's right. Who's not comfortable with binary? Either say yes, no, or I don't know. Binary is base 2. Base 2 is simply what we would look like if we sold fireworks for a living. That's how we would count. Base 2 is, we just count in the normal way, but instead of having 10 digits, we only have 2. So I always like to think of the odometer on a car. So the car starts off at the beginning of the journey looking like this. Suppose we're working in decimal. My car's a hexadecimal car, but suppose you've just got a decimal car. You drive on for a while, and this 0 slowly moves higher and higher, and a 1 starts creeping up, and you drive a bit more, and suddenly it looks like this, 1. Does that make sense? And then we drive a bit more, it's 2. You drive a bit more, it's 3. It's pretty boring for a little while. But if you've got one of the mechanical ones, something beautiful is about to happen. I used to love watching this. When it's 9, it goes, now this is just a wheel. What's on this wheel here? 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So after the 9's there, when I go 1 more kilometre, what's going to pop up here? 0. And what else happens? The next wheel moves on by 1. That's right. And similarly, you rotate round and round and round and round. And when you get to the very biggest number that can be represented, the very biggest digit you've got, then it resets to 0, and the next digit flips up 1. And I used to love it on trips when we got to 9. Because you'd watch it, and then this would flip to 0, and then this, on my old crappy car, then this would flip to 0, and then this would flip to 1. So when you have 2 at the highest digit, does that make sense? That's how a car odometer works. Now, in binary, it's exactly the same. Except we don't have the luxury of, on our wheel, having 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Our wheel simply contains 0 and 1. So we drive along and we go 0, 0, 0, 0, 0, 0, 0. And after 1 kilometre, what does it say? The 0 goes out and we get a 1. Then after another kilometre, what comes in now? 0. This is ticked over. What happens whenever one wheel ticks over? The next wheel ticks on one place. In this case, ticking to 1. Then we drive another kilometre and this one goes to 1. This is the exciting part. It happens so much earlier in the binary car. You go 1 more kilometre, that ticks over to 0, that ticks over to 0, and that ticks over to 1. So, if I was writing the binary numbers out, it'd be 0, 0, 0, 1. This is hopefully going to look a lot like the Martian thing I did before. 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, because that's just ticked over. 0, 1, that ticks over again. That's a 0. Which in computer science, we actually do write like that. Has everyone seen that? If you're a computer scientist, you have to write your zeros like that, except we normally write them a bit slashy. And we write 1s like this, just so we don't get them mixed up with I's. So I've completely stuffed that. 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And Now, okay, the 2 are there. What happens when we tick over another kilometre? It goes 1, 0, 0. Okay. So that's really the number 0. We've travelled 0 kilometres, we've travelled 1 kilometre, we've travelled 2 kilometres, we've travelled 3 kilometres, we've travelled 4 kilometres. And it works out, just like my kids are learning counting at the moment at school, when they write 56, or 156, my daughter tells me, did you know, Dad, that means there's 1 lot of 100. There's 5 lots of 10, and there's 6 lots of 1. And she looks at me like I'm an idiot. And I go, oh, you're pulling my leg. No. And she says, oh, that is pulling my leg, actually. That's 50. So 5 lots of 10 and 6 lots of 1. And then you add them together and that gives you the number. And that's how numbers really work, Dad. Well, this is how that's how decimal numbers work. That's how all numbers work. So this is the number of 1s. That's the number of 1s. This is the number of 10s because takes 10 ticks of the wheel before this moves on 1. It only takes 2 ticks of the wheel before this one moves on, so that's 2. It takes 100 ticks before that moves on, so that's 100. It takes 4 ticks before that one moves on, if you have a look. And basically this is 10 squared, 10 cubed, 10 to the 4th, 10 to the 5th. And similarly going up in binary, the next one, that's 2 squared. The next one's 2 cubed, 2 to the 4th, so on. So if I gave you the number 1, 0, 1, 0, my favourite number of all time, what is that number? Don't call it out. Work it out. That tells you how many 1s, how many 2s, how many 4s, how many 8s, how many 16s. What is that number? I knew I could get someone to call it out. It is 10. Yeah, I like that because it looks like 10, doesn't it? Okay. So does that explain binary? So how do you work out? Oh, no, we still haven't answered Rupert's question though. So, how many bits does a given number take to represent? I'll write it in the same place, but a bit neater. That's 2 to the 3s, 2 to the 2s, 2 to the 1s, 2 to the 0s, which are 1s, 2s, 4s, 8s, 16s, 32s, 2 to the 4, 2 to the 5. Okay, so how do I know if I've got the number 1, 0, 1, 1, 0, 1? What's that number going to be? I know that number is at least as big as 32 because it's got a 1 and 32 columns, so it's 32 plus this. So it's going to be less than 64 because I haven't got anything in the 64s column. So I know if I've got a 1, 2, 3, 4, 5, 6-bit number that it's somewhere in the range of 32 to 64. Or I can say it backwards. If I've got a number in the range 32 to 64, I know it'll take 6 bits to represent. This is called log to the base 2. Who knows about logs? Logs. Who doesn't know about logs? Oh, logs are awesome. What logs tell you is how many digits are in something. So if I'm working in base 10 and I say log to the base 10, what's log to the base 10 of a million? 6. Yeah, how many times do you have to raise 10? What power do you have to raise 10 to get to a million? It's 6. Because there's 6 digits in it. Actually, there's less, isn't there? There's 7. 6 zeros. Yeah. Roughly. Log is roughly how many digits does it take? There's a +1 error, but who cares? We'll never have a problem with that as computer programmers. So similarly, in binary, the question I ask you is to find log of 64 to the base 2, I'm saying when I write 64 in binary, how many bits does it take? And it takes 1, 2, 3, 4, 5, 6, 7 bits. It's 2 to the 6. Aha! Here's my +1 error because I start with 2 to the 0. Okay. So a log is just how many bits it takes to represent something. And your calculator should have a log function on it. Who has a calculator with a log function on it? Who has a calculator? Oh, good. Excellent. Who has a Hewlett-Packard reverse Polish calculator? Oh, you're my friend. Oh, Sue. Hello. Can I have a look at it? Does it still work? Oh, it's emulated. It's emulated. No, I want a real one.
That'd be log 10 though in the calculator.
No, a good calculator will have log 2 as well.
Oh, really?
Yeah. Logs will turn out to be interesting to us for various reasons that we'll see next week. Okay, now I had something else to show you. If there's no more, are there any more questions? Thank you for that question at the back. That was a good one. Did I answer it sufficiently? Yeah. Basically, those that weren't completely sure with binary, do make sure you write out the numbers, say 0 to 64 or 0 to 100 or something in binary, just to make sure you can do it. And then ask yourself a few questions, just as like homework. Say to yourself, oh, what would 107 be in binary? And make sure you can write it in binary and check it out. And then write yourself a number in binary and ask it what is the decimal and check you can work it out. Just fool around with it until you can work it out. And then give it a number, try and work out how many digits it's got in base 10, which is easy. Give it a number in base 10. And then give it a number in base 10, try and guess how many digits it's got in base 2. Just fool around with them a little bit. Just as that can be your homework practice for the weekend. In addition to the other one I gave you of inventing a new sorting algorithm, telling it to me and making me famous. Okay, now let's just return to the lecture slides. Were there any more questions? We have only 5 minutes, so I'll do two things, I think. First of all, a few days ago, Maury, who I know, you had Maury last semester, didn't you? Who's a really, really lovely guy. And I like him, and we joke a lot, and he's fun. And one day, he came into my class, and we wanted to calculate the greatest common denominator of two things. Greatest common divisor, sorry, of two numbers. And there's a famous algorithm called Euclid's algorithm to do that. And you hopefully all learned that last semester. And there's also an algorithm I invented called Richard's algorithm, which is just try all the numbers in turn to see if it's a common factor of both of them and then pick the biggest one. Again, a brute force algorithm. You're hopefully starting to spot a pattern in the sorts of algorithms I pick. And so I wondered if my algorithm run on my incredible Mac would beat Euclid's crappy old algorithm. It's like thousands of years old. And I was going to run it on a Maury. So I made Maury come down and do the calculations in his head to do Euclid's algorithm. And he was slow and made terrible mistakes. He was a joke. But lo and behold, what did we find? I ran Richard's algorithm on a super fast Mac with dual-core Pentiums, 2.8 gigahertz, 2.8 billion instructions per second, and we coded it in C, touted as a super fast language. I ran Euclid's algorithm on a 1 hertz Maury. We coded it in the language slightly confused. Here were the approximate execution times we got. To calculate it, the greatest common denominator of 121 and 55, which was 11, Euclid's algorithm took Maury 1 second. I did it in under 1 second. So we doubled the size of the number. So we're not doubling the numbers, we're doubling the number of digits. Can you see that? Increasing the number of digits. So we're actually increasing the size of the problem. Double the number of digits in decimal, you double the number of binary digits it takes to represent. So we're doubling the information thing. It still took me, how long did it take me? Under a second. It took him 90 seconds. Then I went up by 2 more digits again. It took him around about a minute. That's a bit weird, isn't it? He was speeding up a bit. Thurston was there with a hairdryer on Maury's hair. And again, less than a second for me. Then we made the numbers even bigger. 1.5 seconds for me, 2 minutes for him. And you can see what's going to happen, can't you? Ultimately, it doesn't matter what hardware you run it on, the best algorithm's going to win. Just by doing Euclid's algorithm in his head, once we got to numbers of this size, he was able to do it in 2.5 minutes, and it took me half an hour. So again, just making exactly the same point we made with that film before. Here's my summary point to take away for today. Never fall into the trap of thinking that measuring the time it takes for a program to run tells you something useful about the speed of the algorithm. It tells you nothing about the algorithm. If we wanted to work out something about the algorithm, which you will have to do for your assignment, we have to look at how long it takes to solve given one size problem, the ratio of that to how long it takes to solve a bigger problem. If we double the size of the problem, does it take twice as much? Does it take 4 times as much? Does it take even more? Okay. Absolute speed is irrelevant. We classify algorithms by how the speed changes between different size inputs. Then we've sort of said everything else. Oh, R3 sorts. Yeah. So we looked at selection sort, insertion sort, bubble sort. My homework challenge for you, because I haven't given you any homework yet, is code those 3 algorithms in C over the weekend. Because, gee, that would make an excellent Prac exam question, I reckon. Now, with algorithms, we can basically sort them into 3 groups. This is binary again. Good ones, bad ones, and mediocre ones. In general, good algorithms are ones that run at linear time, at constant time, or maybe have logarithmic time. So if you double the number of bits in the input, it increases by, if you increase the number of bits in the input by 1, it takes 1 more unit to work. So logarithmic is just slightly worse than linear time. Mediocre algorithms are n squareds, are n cubes, that sort of thing. Sometimes they're okay if you're solving small problems, but for big problems you're doomed. For really big problems you're doomed even with a log one, I guess. But generally the good ones are your logs, your linears and your constants. Your mediocre ones are your polynomial ones, your n squareds, your n cubes. And then the bad ones are your exponential ones. Now the word exponential, the phrase exponential complexity seems to have moved into common everyday English. Often people hear people talking about problems saying, oh, that's got exponential complexity, or that's exponential. And 9 times out of 10, when you look at the problem they're talking about, it's actually only quadratic. So don't just use this word lightly. Exponential algorithms you're doomed for. With an exponential algorithm, you give it 1 more bit on the input, it takes twice as long to solve. So you can see you're completely doomed. If your problem takes more than 30 or 40 bits, forget it to describe. So exponential algorithms are really bad. Sadly, most of the naive algorithms we come up with when we think of how to solve a problem will be exponential. They'll work fine for small cases, but for big cases we'll be doomed. Admin stuff. Sample Prac exam question. Oh, I'm not going to give you any clues about the Prac exam at all. Raw wiki notes. Next week, the first tute, the people in the Wednesday 09 tute, your job during the next lecture will be to take notes from the lecture. I will write up nice notes from the 2 lectures this week so you can see what they look like. Your job is to take nice notes next week and post it on the web. Each week a different tute will take different sets of nice notes. By the end of the course we'll have nice notes for the whole course and you'll only have to work at it once. And repeated tute in lecture 4. Lecture 4, which is the lecture we're having now, today it was a core lecture. But usually, after a couple of weeks, for the next 2 weeks it'll also be core, usually it'll run as an extension lecture, which you don't have to come to, and we'll just talk about fun stuff. And so you'll have 2 lectures for the price of 1, and it's like a double feature. And last of all, the repeated tute. If you've repeated this course, if you've previously failed it and you're doing it again for the second time, you're welcome just to be in whatever tute you're in now and leave everything exactly the same. But past experience has shown me that students that fail the course once tend to fail it the second time as well. If you're really keen not to fail it the second time and you have failed it once, I've put on a special tute just for repeater students. It runs on Friday afternoon, so it's a terribly inconvenient time. I've put one of our very best tutors onto the repeater tute. They'll take enormous care of you. In the past, I've run repeater tutes 4 times over the past 10 years. Every time I've run it, no one in the repeater tute has failed. No one has got less than a credit. Normally, repeater students fail. But the deal is, if you turn up to the repeater tute, they'll go more carefully over the things you failed the first time, so you learn them. But the deal is, you don't get any extra marks for going to the repeater tute, but there are extra mark penalties for going to the repeater tute. If the repeater tute people skip tute or lab questions, they get mark penalties applied to their mark. So they're actually treated worse than other students. Yet bizarrely, they do better. So if you're interested in doing that, please contact me. You need permission from me to join that tute. Send me an email. If you're a student that fails the Prac exam next week and you get nervous and there are spaces left in the repeater tute, you can mail me and ask to be moved into that tute as well. See you next week, guys.